So we now move on to Quantum Today, and the next speaker will be John Preskill from Caltech, and the title of his talk is Quantum Computing and the Entanglement Frontier, and it will take him a minute or so to set up his quantum computer. That was beautiful. Thank you. Ready to go? It's all yours.
Thank you very much. Thanks for inviting me to speak here. So as we've heard, Bohr's atom is 100 years old now, but still some of the deep ways in which classical and quantum systems differ from one another we've begun to understand only relatively recently. And some of those differences have to do with the physical properties of information. To a physicist, information is something that we can encode and store in a physical system, like the pages of a book. But fundamentally, all physical systems are really quantum systems, so information is something that we can encode and store in a quantum state. Now, information carried by quantum systems has some notoriously counterintuitive properties. That's why physicists like to speak of the weirdness of quantum theory, and we cherish that weirdness and take great pleasure in it, but we're also asking with increasing seriousness whether we can put the weirdness to work, exploit the unusual properties of quantum information to perform tasks that wouldn't otherwise be possible in a classical world. And that desire to put weirdness to work has driven the emergence of a field we call quantum information science, which derives a lot of its intellectual vitality from three central ideas: quantum entanglement, quantum computing, and quantum error correction. And my goal in the talk is to explain these ideas. In the classical setting, we know any amount of information can be expressed in terms of indivisible units, bits of information. And we might envision a bit as an object like a ball, which can be either one of two colors. And because I like to protect my bits, I can put the bit inside a box. And then later on, when I open the box, the color ball that I put in comes out again, so I can recover a bit and read it. And quantum information carried by a quantum system, can also be expressed in terms of fundamental units, qubits, where for many purposes it's useful to envision a qubit as an object stored inside a box, but where now the box can be opened through either one of two doors, which Bohr would have called complementary. Now we can put information into the box through either door, door number one or door number two, and then later on, if we open the same door again, the color that we put in comes out again, just as though the information were classical. But if we store information in the box through door number one, and then we open the complementary door, then what comes out is intrinsically random and unpredictable, has a 50% chance of being either red or green, even though we know exactly how the qubit was prepared. So to read the information, you have to open the right door. And one consequence of that can be appreciated if we think about copying a quantum state. If I had a quantum copy machine, it would mean that if I happened to have prepared a qubit through door number one, I could copy it and then open door number one on the original and the duplicate, and the color I put in would come out of both boxes. And likewise, if I happened to have put information in door number two, then I could make a copy and open door number two of the original and the duplicate, and the color I put in would come out of both boxes. But in fact, there's no such physically possible machine. We can't, with perfect fidelity, copy unknown quantum states. The reason is that the copier has to probe inside the box. If it opens the right door, everything's fine, but if it opens the wrong door, it will damage the information, and we won't be able to copy it faithfully. So although we might be able to clone a sheep, we can't clone a qubit. The really interesting differences between quantum and classical information can't be appreciated unless we have more than one qubit. Before I get to that, so I want to talk about qubits abstractly for now, but To have in mind a concrete physical realization, you can think about a single photon with information stored in its polarization state, where door number 1 corresponds to measuring the polarization along the horizontal or vertical axes, and door number 2 to measuring along the complementary 45-degree rotated axes. So now let's suppose I have 2 qubits. One's in my lab at Caltech, the other is in the custody of my friend in the Andromeda galaxy. They're very far apart from one another, but a long time ago, both of these qubits were on Earth, and they interacted and became correlated in an interesting way. Namely, I can open my box through either door number 1 or door number 2, and either way, what I find is completely random and unpredictable. And the same thing is true for my friend in Andromeda. He opens door number 1 or door number 2, and finds just a random bit. So neither one of us acquires any information about what's inside the box when we locally open our boxes in Pasadena and Andromeda, but there really are 2 bits of information stored in this pair of boxes. What's unusual here is that all the information is encoded in the correlations between the boxes. Namely, I can open door number 1 in Pasadena and see a random bit, but if my friend opens the same door, he'll always see the same color that I do. And the same is true if I open door number 2 and my friend opens door number 2. If we both open the same door, we see the same random bit. Now, there are 4 distinguishable ways in which a qubit in Pasadena could be correlated with a qubit in Andromeda. We could either see the same color or different colors when we both open door number 1 or we both open door number 2. And we've chosen one of those 4 ways. That's 2 bits of information encoded in the pair of qubits. But what's unusual is that that information is inaccessible locally. It's completely non-locally shared between the 2 distantly separated boxes. And that's the property we call quantum entanglement. It's the really essential way in which quantum information is different from classical information. Correlations themselves are not so unusual. We encounter them all the time. My socks are usually the same color, so when you look at my left foot, you already know without looking what color sock to expect to see on my right foot. And it's almost the same with the boxes. If I want to know what my friend is going to see when he opens door number 1 in Andromeda, I open door number 1 in Pasadena. If I want to know what he's going to see when he opens door number 2, I'll open door number 2 in Pasadena. So it may seem that the boxes are just like the sockses, but that's not right. The boxes are fundamentally different from the sockses, and the key difference is that there's just one way to look at a sock, but we have these 2 complementary ways of looking at a qubit, and that makes the correlations among qubits richer and far more interesting than correlations among classical bits. This phenomenon of quantum entanglement was first explicitly described in Einstein's paper with Podolsky and Rosen in 1935, and to them quantum entanglement was so unsettling as to indicate that something was missing from our quantum description of nature. It seemed to Einstein that if I, by opening door number 1 or door number 2 in Pasadena, can find out what my friend will see when he opens the corresponding door far, far away, it must be that the result of my friend's measurement was really determined all along, contrary to conventional quantum theory. But Bohr disagreed, believing that this was just a particularly stark instance of complementarity. When I open door number 1, I give up forever any possibility of knowing what would have happened if I had opened door number 2 instead. Now, the theory of quantum entanglement did not advance very much for 30 years until in the 1960s we learned from John Bell to think about entanglement in a rather different way, not just as something weird and mysterious, but as a resource that we can use to do things. Bell described a game that 2 parties, Alice and Bob, can play. It's a cooperative game. Alice and Bob are on the same side, and they're both trying to win. And in this game, Alice and Bob receive inputs, and their goal is to produce outputs which are correlated in some way that depends on the inputs that they receive. But under the rules of the game, they cannot communicate between the time they receive the inputs and they produce the outputs. They can use correlated bits, which they share that were prepared ahead of time when they play the game. But even so, if they play their best possible strategy, they can only win the game with a probability of success of 75%, even using that correlated information averaged over the inputs that they receive. But if, before the game began, quantum correlations, entangled qubits, had been distributed to Alice and Bob, then they'd be able to play a better quantum strategy and win the game with an improved probability of success, a little above 85%. And experimental physicists have been playing this game for over 30 years now, and they keep winning. So it seems these super strong quantum correlations are really part of nature's design. Einstein derisively described quantum entanglement as spooky action at a distance, and that sounds even more derisive when said in German. But it's just too bad for Einstein, because nature is as experiment reveals her to be, and we just have to learn to love her as she is. So boxes are not like soxes. You can use entanglement to win a game with a higher probability of success. Is that really a big deal? Yes, it's really a big deal. And to appreciate why it's such a big deal, we should think about quantum systems with many parts, just not just two. So, for example, I can imagine a book. It's many pages long. It's got 100 pages. If it were a classical book, there'd be print on every page. I could read 10 of the 100 pages, and then I would know 10% of the content of the book. But suppose it's a quantum book. Each page is a quantum system, and the pages are highly entangled. What that would mean is that if I look at 10 pages of the book, I'd learn almost nothing about the content of the book. That's because information isn't printed on the individual pages. Almost all the information is in the correlations among the pages, and if I want to read the book, I will have to collectively read many pages at once. I could have a relatively modest number of qubits, just a few hundred or so, and if I wanted to describe in terms of classical bits all the correlations among the boxes between whether I would see red or green if I opened the boxes through door number 1 or door number 2, describing all those correlations classically, I'd have to write down more bits than the number of atoms in the visible universe. It'll never be possible, even in principle, to write down that classical description. And that property of quantum information, that we can't succinctly describe it classically, was very intriguing to Richard Feynman, and it led him to make the suggestion over 30 years ago that if we built a quantum computer which processes qubits instead of bits, it should be able to perform tasks that we could never do with digital computers. If we can't even describe classically the content of the quantum computer, then by processing the qubits, perhaps we can do things that we couldn't do with digital computers. And around the time Feynman was making that suggestion, Peter Shor was an undergraduate at Caltech studying mathematics, and like all Caltech sophomores, he took a course on quantum physics, the most advanced physics course he took, but like most Caltech sophomores, he remembered what he learned and drew upon it some years later to make a remarkable discovery, an example of a problem that we think is hard for digital computers, although there's no proof of this, is finding the prime factors of large composite integers. But what Shor discovered is that if we had a quantum computer, this would be an easy problem. It's not much harder than multiplying two numbers together to find their product. So in the quantum world, the boundary between the hard problems and the easy problems, the ones that we'll never be able to solve and the ones that we can solve with advanced technology, is different than it would have been if the world were classical. So we can state this as a criterion for how the resources needed to solve the problem scale with the input size. About the hardest factoring problem we can solve nowadays is 193 digits. It can be done in a matter of months by a network of hundreds of workstations. But if we use that same hardware and the same algorithm to try to factor a 500-digit number, it would take longer than the age of the universe. But suppose we had a quantum computer. We don't have this yet, but suppose we had one that had the same clock speed as that classical computer. It could perform the same number of elementary operations per second as the classical computer. It would be able to factor the 193-digit number in 1/10 of a second and the 500-digit number in 2 seconds. there's a vastly different scaling of the resources we need to solve the problem with its input size in the quantum world. Does anybody care about factoring? Yeah, a lot of people care about factoring because the difficulty, presumed difficulty of factoring and other number theoretic problems is the basis for the public key crypto systems that we use today to protect the privacy of our financial transactions. When quantum computers are readily available, we won't be able to use those same protocols. Alternatives exist, but it's not exactly clear what will be the best way to protect our privacy in a post-quantum world. The important thing that we learn from Shor is that there's an interesting classification of problems, and in particular, these problems of intermediate difficulty, which are hard for classical computers but easy for quantum computers, and it's an important theoretical problem to understand what's in that region. And quantum computers have limitations. We have to have a problem which in some sense has a structure which is well suited for quantum computation to be able to enormously speed up the solution. In particular, we don't think that for the NP-complete problems, at least in the worst case instances, that we can get a very dramatic speed up with a quantum computer for problems like satisfiability or the traveling salesman problem. But on the other hand, there are problems that are not in NP, problems that we can't check the solution with the classical computer, which are interesting and which quantum computers can solve. And perhaps the most natural and important of those problems that we know of is the one that Feynman originally had in mind, simulating the evolution of many particle quantum systems. That's something we can do with the quantum computer. So, for example, in strongly coupled quantum field theory, it seems to be a hard problem to classically simulate real-time processes like particle collisions, but with a quantum computer we would be able to do that with resources that scale in a reasonable way, with the total energy of the process, with the number of particles produced, and with the precision that we want to attain. So quantum computers would be very interesting. Why don't we have them already? What's the delay? Well, you see, it's really, really, really hard. And one of the reasons it's hard is that we need to overcome a formidable enemy, decoherence. Physicists like to speak about a quantum state of a cat, which is the superposition of the live and dead state of the cat, but we never see such superpositions of macroscopically distinguishable states because we can't prevent any real cat from immediately interacting with its surroundings, which in effect measures the cat and projects it onto a completely dead or completely live state. And that phenomenon of decoherence is the key to understanding why quantum mechanics holds sway at the microscopic scale of atoms, but is not relevant to the observations of ordinary, everyday macroscopic systems. A quantum computer will be a lot different than a cat, but it too will, even though we try to avoid it, interact with its environment, which can cause it to crash. So we can't get a quantum computer to work properly unless we can protect it from decoherence and other sources of error. Errors are a problem even classically. I have bits that I want to protect. Everywhere there are dragons lurking who delight in tampering with our bits. But one way in which I can protect my bits in the classical world is by storing them redundantly. I can have backup copies of the bit, and then the dragon might be able to flip one of the bits, but if he hasn't flipped more than one out of the three, I can employ a busy beaver who checks and makes sure that all three bits are the same color, so I could protect the bit from damage because it's been redundantly stored. And we'd like to be able to use the same idea that redundancy provides protection for quantum systems, but things aren't quite so simple because we can't copy unknown quantum states and store a backup copy of the state of a quantum computer. And furthermore, there are more things that can go wrong in the case of qubits than bits. It could be that the dragon opens door number 1 and flips the bit. That would be like a bit flip in classical data. But alternatively, the dragon might instead open door number 2 and flip the color of the bit. And that's what we call a phase error in the quantum state. And phase errors are particularly troublesome because another way of thinking about them is that the dragon could open door number 1 and instead of flipping the bit, he could just remember the bit or keep a record of what he saw. And that too would cause an error if we observe the qubit through door number 2. And because it's easier typically to remember a bit than to flip a bit, these phase errors are particularly pervasive and occur in many quantum systems at a high rate. So if we want our quantum computer to work, we have to hide the state of the quantum computer from the environment. If a quantum computation was successful, then it should be that if we ask the quantum computer afterward what it just did, it gives the answer, I forget. There should be no record left behind. There's a record of the final result of the computation, which we can broadcast, but no one should be able to know the state of the quantum computer during intermediate stages of the computation. That must remain a well-encrypted secret. And in fact, there are ways of encoding the information in entangled states such that the information can be well hidden. I can take a single qubit, for example, and encode it in an entangled state of 5 physical qubits in such a way that, just like one of the pages in that 100-page book, if the dragon makes any observation on one of the qubits, he can't learn anything about what the encoded state is. And in fact, he doesn't damage the state because we can get a beaver to come along and check the way the qubits are correlated with one another, and if those correlations have been disturbed, they can be restored so the original encoded quantum state is undamaged. So we really can redundantly store quantum information so it can be protected. In 1997, I met Alexei Kitaev, and that day when he gave a talk and I made these notes was one of the most exciting days of my scientific life, because what I heard from Kitaev I recognized as a potentially transformative idea about quantum error correction. What he pointed out is a connection between quantum error correction and topology. To a mathematician, topological properties are the properties that stay invariant if we smoothly deform an object without tearing it. And for a quantum computer, we would like the way it acts on protected information to remain invariant if we deform the computer by introducing some noise. And physicists know of topologically invariant physical interactions, like the Aharonov-Bohm effect. If I consider the phase acquired by an electron that's transported around a magnetic flux tube, that phase remains invariant if I deform the trajectory of the electron while maintaining the topological invariant, its winding number, around the tube. And if I consider particles in two-dimensional systems, there are more exotic varieties of these Aharonov-Bohm interactions. There can be particles called anyons, where, first of all, if there are many particles, there are many quantum states which locally look indistinguishable. So there's a big Hilbert space of states which can be very well hidden from the environment, and those states can be processed by performing exchanges of the particles. Even though the particles never come close to one another, the quantum state changes because of Aharonov-Bohm phenomena. So we can envision operating a topological quantum computer where we initialize by preparing pairs of anyons and perform a sequence of exchanges of the particles so that their world lines trace out a braid in 2+1 dimensional space-time, and then read out the computer by bringing the anyons together to see whether they'll annihilate or not. And the beauty of this idea is that if we keep the temperature low and the anyons stay far apart from one another, except at the very beginning and the very end, then the computation is intrinsically robust. The information that's being processed is encoded very non-locally, very well hidden from the environment, and in principle, if we carry out the right braid, we'll get the right answer to the computation. At least that's how it looks to a theorist. But in what type of physical system can we realize these ideas? What now seems to be the most promising possibility is also due to an idea of Kitaev from some years ago, which is that in certain kinds of quantum wires, an electron can be split in half. In particular, there are two types of superconducting wires, what we might call the conventional superconductor and the topological superconductor, and these two phases are separated from one another by an object we call a Majorana fermion, which you can think of, roughly speaking, as half of an electron. And if we introduce an extra electron which tunnels into the wire, it can in effect dissolve or split up. and the state of the Majorana Fermions will change. So there are two quantum states which differ by whether the total number of electrons is even or odd, but locally they look the same. So this is a good way of topologically protecting quantum information from the environment. And in the last year or two, the first experiments have been done indicating that this type of splitting of an electron that tunnels into the wire can occur, but more definitive experiments will still need to be done before the idea gains universal acceptance. So if we have such Majorana fermions in quantum wires, can we use them for processing? Well, we can, in fact, exchange them like we would exchange anyons in a two-dimensional system. I can move the Majorana fermion with voltage gates, with electric fields, so that I can take one of them and park it around the corner of a T-junction, move the Majorana fermion from the right to the left, and then unpark the first one. So we performed an exchange, which is a way of processing the topologically encoded information. Now, this type of braiding of Majorana fermions has not been achieved experimentally, but we're hopeful that it can be in the next few years. And if that happens, it will be a milestone for physics, aside from any technological implications it might have in the long term. So is this really the right way to build the hardware of a quantum computer? Well, we certainly don't know that at all, because there are a number of other approaches to building hardware that are being aggressively pursued and are making good progress. One is to have our qubits be encoded in the internal states of atoms in an ion trap. Another is to use the spins of single electrons and quantum dots. Another is to use qubits which are encoded in quantum circuits with a lot of nonlinearity. And in all these cases, we can get the qubits to interact with one another in a controlled way. For example, in the case of an ion trap, we can use the motional states of the ions as a means of getting ions to talk to one another. In superconducting circuits, we can use their coupling to microwave cavities. So with any of these types of hardware, we can, if we want to scale the system up to many qubits and many operations, use the idea of quantum error correction. And the best idea we have now is to essentially simulate topological matter in which there's a system with a degenerate ground state, and the different ground states look alike locally but are globally distinct, so that information can be very well protected. In order to get that to work, the hardware has to be sufficiently reliable. Nowadays, the state of the art is that we can do operations on of order 100 qubits with an error per gate, which is at about the 1% level. We would like to get the error rate down by an order of magnitude, and it'll still be a tremendous physics and engineering challenge to scale things up to thousands of qubits and millions or billions of operations, as we would eventually like to do. So in quantum information science, we're addressing a number of challenges: how we can use quantum states in cryptography, which I didn't really have time to talk about. What problems can we solve on a quantum computer? How can we protect quantum states? How can we build hardware? But I'm not an engineer, I'm a theoretical physicist, so I'm most interested in the ways in which ideas about quantum information can have a broad impact on science. And a lot of those broad implications have to do with what we call the monogamy of quantum correlations. Classical correlations are polygamous. They can be shared in many ways. Alice and Bob can both read the same daily newspaper, and that means they become correlated with one another, but nothing prevents Carrie from reading the paper also and sharing their correlations with both of them. But quantum correlations are different because they're harder to share. If Alice becomes fully entangled with Bob, that prevents Bob from being at all correlated with Carrie, and likewise, if Bob decides to be fully entangled with Carrie, he can't be at all correlated with Alice. So we speak of the monogamy of entanglement, and this monogamy is very frustrating for Bob in particular, who might want to highly entangle with both Alice and Carrie. But it also has many implications. For example, in cryptography, Alice and Bob can use entanglement to distribute a key for secret communication, and because they're highly entangled, Carrie can't be correlated with them and therefore can't eavesdrop on their secret communication. It's very important in the study of quantum matter. If I have a system with many particles, all of which want to be mutually entangled, they have to find some suitable compromise in how that entanglement is shared, and that gives rise to different patterns of entanglement in quantum many-particle systems which have universal properties which we can use to distinguish different quantum phases of matter, and we're learning a lot about that in just the last few years. Monogamy is even important in black hole physics, where the radiation coming out of a black hole wants to be highly entangled with radiation that was emitted a while ago and with degrees of freedom behind the black hole horizon. And we still don't understand very well how black holes resolve that conflict. That's the firewall puzzle, which will be the subject of a session this afternoon. So at Caltech, we have an Institute for Quantum Information and Matter, and our logo does homage to Bohr. It is supposed to evoke the idea that the observer is an active participant in quantum measurement. Each one of the letters is only half there, and you, the observer, complete the letters through your act of observation. And the goal of the IQIM is to explore an emerging frontier in physics. It's not the frontier of very short distances, as in particle physics, or very long distances, as in cosmology. It's a frontier of complexity, an entanglement frontier. We want to scale quantum systems up to larger and larger size, hoping to attain quantum supremacy, the ability to get controlled quantum systems to do things that we couldn't possibly simulate classically. And we have a motto, nature is subtle, which evokes the statement of Einstein, subtle is the Lord, but malicious he is not. Einstein actually underestimated the subtlety of nature when he derisively spoke of entanglement as spooky action at a distance. And in quantum information science, we relish, explore, and exploit the glorious subtlety of the quantum world in all its facets and ramifications. Since this is Bohr's day, we should give him the last word. Bohr, well ahead of his time, was on Twitter and has many memorable tweets. One of them, directed at his friend, is Einstein, stop telling God what to do. And another, equally memorable, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet, as true today as it ever was. Thanks a lot for listening to me.
While we are giving people time to go to the microphones, I have a question for you.
Yeah.
Can you please pronounce spooky action at a distance in German for us?
Well, let me...
So I have stumped the chump.
Just for everyone's guidance, spukhafte Verwirkung.
Very good. I see we have a question.
Hi, I think that you didn't tell us how you could get a quantum computer to just do a simple calculation like 2 + 2. Can you say how that would work?
Yeah, of course that would be a rather that's not the ideal use of a quantum computer, but indeed.
John, she didn't ask you to actually do that calculation, so you don't have to be so nervous.
But as with a classical computer, we can take the algorithm we want to run and compile it and decompose it into a set of elementary steps, each of which, say, acts on a pair of qubits. So as with a classical computer, there's a set of universal gates, and if I can do an AND gate, I can evaluate any Boolean function. In a quantum computer as well, there's a notion of a universal gate. If I can perform a certain unitary operation on a pair of qubits or some set of unitaries on a pair of qubits, I can from them build up an arbitrary unitary transformation, or at least a very good approximation to any unitary transformation acting on n qubits, and that allows me to do any quantum computation.
Thank you.
We have a question from the middle.
I've assumed that there are 129 fundamental matter and force particles, including an electron and an up quark. I've also assumed you cannot split fundamental matter particles. You mentioned splitting an electron. Did you mean that literally?
Well, I didn't mean it literally, but I did mean it in the sense that there can be collective phenomena involving many particles in which electrons can fractionalize. This is a familiar phenomenon in particular in fractional quantum Hall physics, where the system is composed of ordinary electrons, each of which has charge E, but because of collective effects having to do with the state of the many electrons being highly entangled, there can be locally observable quasi-particles which carry charges which are a fraction of the electron charge, like E/3. There's always some compensating charge far away, but that's what I'm talking about, that type of charge fractionalization.
So let's thank John again for a beautiful talk.